Imagine you're a photon of light. You leave the surface of the sun, travel 93 million miles through the vacuum of space, pass through Earth's atmosphere, bounce off this page, and enter someone's eye. From your perspective as that photon, how much time just passed? Here's the thing that'll blow your mind: zero. Absolutely zero. No time at all. To you, the photon, you left the sun and arrived at the eye in the same instant. Time didn't just slow down for you. It stopped completely. And this isn't some philosophical riddle or poetic metaphor. This is what the mathematics of relativity actually tells us happens. So let's figure out why the universe works this way and what it really means. You've probably heard that nothing can go faster than light. That's the cosmic speed limit, right? Light travels at about 186,000 miles per second, or if you like metric, about 300,000 kilometers per second. That's fast enough to circle the Earth 7.5 times in 1 second. But here's what most people don't realize. The speed of light isn't just some arbitrary speed limit the universe picked out of a hat. It's deeply connected to the nature of space and time themselves. And when you really understand what's happening, you'll see why time has to stop for light. It's not a choice. It's inevitable. Let's start with something Einstein figured out when he was working as a patent clerk in Switzerland. He asked himself a simple question: what would you see if you could run alongside a light beam at the speed of light? Would you see the light wave frozen in space, like a surfer riding alongside a perfect wave? That question bugged him for years, and eventually he realized something profound. You can't run alongside a light beam. Not because you're not fast enough, but because the universe won't let you. And the reason has to do with how time and space are woven together. Here's the key insight. Time isn't absolute. It doesn't tick at the same rate for everyone everywhere. If you're moving, time runs slower for you compared to someone who's standing still. This isn't science fiction. We've measured it. Atomic clocks on airplanes run slightly slower than atomic clocks on the ground. GPS satellites have to account for this time dilation, or your maps would be off by miles. The faster you move through space, the slower you move through time. And this relationship is mathematically precise. Now imagine you start walking. You're moving through space, so time slows down for you, just a tiny, tiny bit. You'd never notice it. Now imagine you're in a car going 60 miles per hour. Time is running even slower for you, but still, the effect is incredibly small. Now imagine you're in a rocket going half the speed of light. Now we're talking. Time for you is running noticeably slower than time for someone on Earth. If you could look out the window and see Earth, everything there would appear to be happening in fast forward. And if people on Earth could watch you, you'd appear to be moving in slow motion. So what happens when you reach the speed of light? Time doesn't just slow down a lot. According to the mathematics, time stops completely. The equation that describes time dilation has the speed of light in the denominator. When your speed equals the speed of light, you're dividing by zero. And mathematically, that means time dilation becomes infinite. Time stops. But here's where it gets really interesting. Why does this happen? Why is there this strange trade-off between motion through space and motion through time? The answer is beautiful. You're always moving through space-time at the same total speed. Always. Right now, as you're sitting still, you're moving through time at maximum speed. Every second, you age 1 second. That's what it means to be stationary. You're moving through time, but not through space. But the universe has this rule: your total motion through space-time is constant. Think of it like this. Imagine you're walking north at 3 miles per hour. That's your total speed. Now you start walking northeast instead. You're still walking at 3 miles per hour total, but now some of that motion is going east and some is going north. The more you turn east, the less of your speed is going north. If you turn completely east, all your speed is going east and none is going north. Motion through space-time works the same way. When you're standing still, all your motion is through time. You're going north if north is time. When you start moving through space, you're turning a bit east. Some of your motion that was going through time is now going through space instead. The faster you move through space, the more you're turning, the less motion you have through time. And if you could reach the speed of light, you'd be going completely east. All your motion through space-time would be through space, and none would be through time. Time would stop. And here's the kicker, light is already doing this. Photons don't have a choice. They're massless, and the universe forces massless things to travel at the speed of light. Always. No exceptions. A photon can't slow down or speed up. It's born moving at light speed, and it dies moving at light speed. And because it's moving through space at maximum speed, it has zero motion left over for time. From the photon's perspective, time doesn't exist. This raises a bizarre question. If time doesn't pass for a photon, does it even experience existence? Think about it. The photon leaves a star 1 billion light years away. From our perspective, watching from Earth, that photon travels for 1 billion years before it reaches us. But from the photon's perspective, no time passes. It's created and destroyed in the same instant. The entire journey, from its point of view, takes 0 seconds. So does the photon experience anything? Does it have a perspective at all? Physicists actually say that asking about a photon's perspective doesn't quite make sense. The math of relativity breaks down when you try to transform into the reference frame of light. It's like asking what's north of the North Pole. The question itself doesn't have an answer because the framework we're using doesn't apply there. But we can get arbitrarily close. We can ask what things look like if you're going 99.9999% the speed of light, and the answer is time is almost stopped. And you'd cross the galaxy almost instantaneously from your perspective. Let's make this concrete with a thought experiment. Imagine you have an identical twin. You board a spaceship that can go incredibly fast, and you zip off to a star 10 light years away. From Earth's perspective, this journey takes 10 years to get there, and 10 years to get back if you're going just under the speed of light. But on your spaceship, time is running much slower. If you're going fast enough, maybe only 1 year passes for you on the journey out, and 1 year on the journey back. You return to Earth having aged only 2 years. Your twin has aged 20 years. This isn't a trick. This is what actually happens. It's called the twin paradox, though it's not really a paradox once you understand relativity, and we've verified this with particles. Muons are unstable particles created when cosmic rays hit the upper atmosphere. They decay so quickly that they shouldn't make it to Earth's surface before falling apart. But they're moving so fast that time slows down for them. From our perspective, they live longer. From their perspective, the distance to Earth's surface is shorter. Either way you calculate it, they make it to the ground. We detect them. The math works. So now let's push this to the extreme. What if you could build a ship that goes 99.999999% the speed of light? At that speed, time dilation is enormous. You could travel to a galaxy millions of light years away, and from your perspective, the journey might take a few years. But when you arrive, millions of years have passed back on Earth. Everyone you knew is dead. Civilizations have risen and fallen. And if you tried to return, millions more years would pass. You'd be a time traveler to the future, unable to ever return to your own time. And if you could somehow reach exactly the speed of light, time would stop completely. You could travel to the edge of the observable universe, and from your perspective, no time would pass. Of course, you can't actually do this if you have mass. It would take infinite energy to accelerate you to light speed. The universe forbids it. Only massless things like photons can go that fast. Now, here's something that'll really twist your brain. From the photon's perspective, the universe is flat in the direction it's traveling. As you approach the speed of light, distances contract. This is called length contraction, and it's the flip side of time dilation. If you're on that ultra-fast spaceship, the galaxy ahead of you looks squashed, compressed in the direction you're traveling. At the speed of light, distances in the direction of motion shrink to zero. So from the photon's perspective, the entire universe along its path is compressed to a single point. It's everywhere along its path simultaneously, created and destroyed in the same moment, occupying no space and experiencing no time. Let's pull back and think about what this means. We live in a universe where time and space aren't fixed, absolute things. They're flexible. They bend and stretch depending on how you're moving. And this isn't just theoretical. Every time you use GPS, you're relying on engineers who accounted for time dilation. The satellites are moving, and time runs differently for them than it does for you on the ground. If we didn't correct for this, GPS would fail in minutes. But here's the part that really gets me. Why is the universe like this? Why is there a speed limit at all? And why does time stop at that speed? Einstein's theory tells us that this is how the universe works, and the math is incredibly precise. But why? One way to think about it is that the speed of light isn't really about light at all. It's the speed of causality. It's the speed at which cause and effect propagate through the universe. It's the speed of information itself. Imagine you're floating in space and you wave your hand. How does the universe know your hand moved? Information about that movement has to propagate outward, and it turns out that information can't travel faster than light. If it could, you'd get all sorts of paradoxes. You could have effects happening before their causes. You could send messages backward in time. The universe would be a logical mess. So the speed of light is really the universe's way of keeping things consistent, keeping cause and effect in the right order. And because the speed of light is the speed of causality, and because space-time is this unified thing where motion through space and motion through time trade off, you get this beautiful consequence. At the speed of causality, time stops. At the speed where information propagates, there's no time to propagate through. It's instant from the information's perspective. Let's think about light again. Light is an electromagnetic wave, or you can think of it as a stream of photons, which are the quantum particles of light. Maxwell figured out in the 1800s that light is electricity and magnetism dancing together, creating waves that propagate through space. A ND. When he calculated how fast those waves should move, he got a specific number, 300,000 kilometers per second. That number popped out of the equations. It wasn't a guess. And Einstein realized that this speed was special. It was the same for everyone, no matter how they were moving. That's the really weird part. If you're standing still and you measure the speed of a light beam, you get 300,000 kilometers per second. If you're in a rocket ship moving at half the speed of light and you measure the speed of the same light beam, you still get 300,000 kilometers per second. The speed of light is constant for everyone. And this constancy is what forces time and space to be relative. Think about it. If you're moving toward a light source, you'd think the light would appear to be coming at you faster, right? Like if you run towards someone throwing a ball, the ball seems to come at you faster. But light doesn't work that way. No matter how fast you move toward the light source, the light still approaches you at exactly 300,000 kilometers per second. The only way this can be true is if time and space themselves adjust. Time slows down for you, and distances contract in just the right way so that you always measure light moving at the same speed. So here's the deep truth. The universe has to work this way. If the speed of light is constant for everyone, then time must be relative. There's no other option. And if time is relative, and time slows down the faster you go, then at light speed, time must stop. It's inevitable. It's not that the universe decided to make things weird, it's that the universe is consistent. And this weirdness is the consequence of that consistency. No. W. Let's talk about what this means for our understanding of reality. We think of time as this thing that flows like a river, past, present, future. We're all moving along in the current, but relativity tells us that's not quite right. Time doesn't flow the same for everyone. Your present moment isn't the same as someone else's if you're moving differently. In fact, space-time is more like a block. All of time exists at once, like a giant four-dimensional structure. What we perceive as the flow of time is just our path through this structure, and light, massless and forever moving at maximum speed, doesn't move through time at all. It's spread across space-time in a different way than we are. We're crawling through space-time, experiencing time second by second. Light blazes across space, experiencing nothing. Here's another way to think about it. You know how you can't accelerate forever because you'd reach the speed of light and that would require infinite energy? Well, there's a flip side to that. Light can't slow down. A photon doesn't experience acceleration or deceleration. It's created at light speed when an electron drops to a lower energy level or when charged particles accelerate. It travels at light speed, and it's destroyed at light speed when it's absorbed by another particle. That's its entire existence. And in between creation and destruction, from its perspective, no time passes. So what happens when light travels through different materials? Light slows down in water or glass, right? Well, not exactly. The photons themselves still move at the speed of light. But when light enters a material, the photons interact with the atoms. They're absorbed and re-emitted over and over. This absorption and re-emission process takes time, so the overall progress of the light through the material is slower. But each individual photon during its brief existence between absorptions is still moving at the speed of light and experiencing no time. Let's zoom out. The universe is about 13.8 billion years old. That's how much time has passed for the average stationary particle since the Big Bang. But for a photon that was created in the early universe and has been traveling ever since, no time has passed. From the photon's perspective, the Big Bang and the present moment are the same instant. And if that photon travels forever into the future, even trillions of years from now, it's still the same instant. The entire history of the universe, from a photon's perspective, is simultaneous. This leads to something beautiful and strange. We live in a universe where time is not absolute, where motion through space means motion through time slows down, where the fastest possible speed is also the speed at which time stops. All of this comes from a simple principle: the speed of light is constant for everyone. That one fact reshapes our entire understanding of space and time. Feynman used to say that the beauty of physics is that you start with a simple idea and follow it logically, and you end up somewhere utterly unexpected. That's what happened here. Einstein started with the idea that the laws of physics should be the same for everyone, moving or not. And Maxwell's equations said that light moves at a certain speed. So Einstein asked, what if light moves at that speed for everyone, no matter how they're moving? And when he worked through in mathematics, he discovered that time must be relative. He discovered time dilation and length contraction. He discovered that mass and energy are equivalent. He discovered that space and time are unified into spacetime. And he discovered that at the speed of light, time stops. None of this was obvious. You can't experience it in your daily life because the speeds we move at are so slow compared to light. But it's real. Every high-energy particle accelerator proves it. Every GPS satellite proves it. Every cosmic ray that hits the atmosphere proves it. Time is relative. And for light, time stops. So next time you turn on a light switch, think about the photons streaming out of that bulb. From their perspective, they're created and destroyed in the same instant. They don't experience the journey from the bulb to your eye. To them, it's instantaneous. But to you, watching, those photons traveled at 300,000 kilometers per second, taking a few nanoseconds to cross the room. You and the photon are living in the same universe, but you're experiencing it completely differently. And that's the wild, beautiful truth about our universe. Time isn't what you think it is. Space isn't what you think it is. They're woven together into something more fundamental, and how you move through space determines how you move through time. Push that to the extreme, move at the ultimate speed, and time stops, not because time is fragile or mysterious, but because that's what the mathematics of a consistent universe demands. And the universe, as Einstein showed us, is nothing if not consistent.